like we're good to go. So last time we talked about doing a carrier look ahead situation. Um, and we mentioned we could ideally, if we really wanted to, create a two-level logic, but that has a lot of complexity issues that go into it. And the big problem is spatial complexity can be really bad. And essentially we said we kind of into connected with that spatial complexity with space, it's also current. So we're going to have huge problems with what's called fan in and fan out. So, anything that those terms mean, fan in, fan out, and fan out refers to current in and out from the transistor or gate or some other device or again. Think of it as you have a bunch of wires coming into your input. So since you've got a bunch of lines coming in, each one carries some amount of current, you have to be able to stick that current. Right? So essentially it's all coming in, you gotta be able to pick it to where it needs to go. Too much current means too much power, means too much heat, which means you burn. For fan out, same idea just on the output side. Okay, so potentially my gate or transistor, or whatever, could have to feed a whole bunch of other devices downstream from me. And each one of them is going to take part of the current that I'm sourcing to them. So I have to be able to set that and keep my signal good. Well, if I have too many loops on it, I'm going to lower down. Each one's going to take part of that current, right? And that's gonna loop my system down, which means my voltage drops, and at a certain point, your signal doesn't carry through, right? So you have to be able to supply all those things that are downstream. If you can't extend the signal, you just push it all. That makes sense? So whenever we're talking about fan in and fan out, we're talking about a particular device. Can it handle the eventual inputs to it, or can it handle the inputs? That is basically just from the two sides. All right. You just want to be used to the names. When you go out to do an interview, having something basic sound, what do they need? Yeah, intelligently talk about them. You know the idea. You just want to make sure you communicate it well. All right. Let's see. Grab a phone. And here we go. So now we want to talk about block, carry, look at. Anybody remember what we talked about at the end, how this was going to work? We stepped it at one level to make it easier to handle. And something that started with G and something that started with P. Generate and propagate. Right? What was generate? Yeah. We just call it usually G sub whatever the base bit is. Propagate is P sub unit. Generate means at that particular bit, there will be a carry that is generated. It doesn't matter what it happens. Right? Yeah, we know we will get a generator because again, remember we've got carry it bit I or whatever propagate. Oh, sorry, X at gate I. I have to go back to the original problem. And Y at gate I, whatever you call them. I sorry, sorry. I've got like an answer so put up above this. So I deface this so I can now find my edge. So we've got at any bit I, right? We've got this for every single bit. It's carried on previous stages. And there's two new bits for that, two changes. X's, type bit, and J's, type bit. And you're going to be adding all those proportional ones. So this is a particular bit. And it'll generate, some at bit I carry from plus one. That was the idea that we had for these. Yeah. Okay. Um, when we're doing this, right, we're trying to find out when this, can I tell you advance what's coming here? And I'm going to get a period, we said whenever two or more of these three bits are true. So if both of these are true, I don't even have to wait for this. That can be unknown. If both of these are true, then I know I will generate something. So that's what becomes our case here, right? Xi and yi. Good? That makes sense. Now, to propagate, that means when will this one get this CI, if it is true, when will it get carried through, right? And if either of these is a one, then it's going to get propagated forward. Now, technically speaking, we could say that means that I've got, you know, since I'm saying either of these, I've got two possibilities, xi, yi, and I could put here for my operation. What are the two potential ones I could put? XOR is one. What else could I use? Or, right? Why is it not one? Since those are different. And I probably about this, and I hear that all people will get very on this one. So we point case, right? So when I'm looking at this, you, four possibilities, right, for your xi and your yi, and 0, 0, 0, 1, 1, 0, 1, 1. Generate takes care of this case. Right? And it doesn't matter we must. So in truth, what is also complicated here, yeah, but it doesn't matter. Really, right? So you could say generate and propagate if it makes you happy, and just know generate is here. So this is true for generate, and who cares about these? But that means I technically don't care here for propagate because generate is true. So I only care about those two in the middle, which means I can't really tell the difference between here. So what should I do? Which one is better? And whichever one makes my life easy, right? That's really what it comes down to. And it's going to be a little different depending on the situation. Or the times when XOR might be easier. Well, in each of these bits, I could do this addition here, but if I consider it, right at the start, and I've got, whatever xi and yi, I'm not going to have to worry about the subtractive bit coming in. I could just put a half adder here. Right? It's going to have a sum bit, which will be XOR. And it's going to have a carry bit coming out, and that one's going to be AND of those two bits. So technically speaking, this is generate, and this could be considered propagate if you use the XOR version of it. Let's throw the legit half out should turn out pre-taken care of me. I have to do the XOR in that case anyway, because there's no way I can get the proper sum bit. Otherwise, I'm going to mess up my average. So I have to have XOR. So I might as well take it. It's free. Right? That makes my life easy. That makes it a smaller design, all kinds of nice stuff. Now, what if I didn't have which one would be easier? XOR or why is OR better? It is, but why? How the gate is constructed. I agree with you on that one. It is a much simpler gate, which means it's smaller than that gate, and therefore it has a slightly faster propagation. So the time an XOR is usually 1.5 organs, equivalent A, before you get the answer. So OR is a little bit smaller and a little bit faster. So in general, we can, um, um, but if the guts something, it'd be crazy not to take advantage of it. Does that make sense? So our basic idea at this point is we're going to have kind of a bunch of these half adders, and we're going to repeat this for every single bit. I'm just going to put 3 dots in both directions to just say I'm going to do that at all times. The outputs generated propagate. That's my input. Right? The generator is also going to be an integer carry generated that, but I don't need it anymore. You have to worry about the carries coming out of it being the generator, right? So the next one is going to be meter generator. It's going to take it overhead system. So I'm going to worry about ordering that. But I'll get this, which will go out as generate and propagate to my system. But this propagate is also a temporary sum. In between, right? Maybe I'll put TS for a temporary sum because this was the sum of these two. And then I have to add it together with a carry in that is actually going to come from whatever this block carry look ahead will do down here. Or carry look ahead if you made it big enough. Uh, it's got to add these two. And I could care less about that carry out there because I don't need it anymore. It's already going to get taken care of by this system. So this is unneeded. So I just put that X there. Maybe you shouldn't do that because I've got up here. Maybe I'll just, garbage, whatever you want to think of it, garbage can or something. You don't need what of this heat fender. But the sum bit coming out, ooh, I want to go there. This is the actual sum bit I. This is an output we care about. Doesn't go to the block here. So it's just trying to get what's in that box. Does it make sense what we're kind of doing on this? And then this block carry look ahead is going to generate all of these carries for me. And you need to know that carry in for the overall system. Yeah. Because it needs to know that to handle propagate. We'll tell it, will it propagate to this thing or not, or pass my level? Well, that's going to depend upon whether or not it's propagate. But we'll handle all the carry-ins and carry-outs. Good? So this is the basic idea. This here is actually what you do. The whole, this gets repeated at every bit. That's how you get some, right? And just each bit, notice they're independent of the other. The only connection is happening down here. Every bit will get generated. Okay? Now, this, maybe I should put this in parentheses as a block. This is a carry look at. If I do all the bits in one device, then it's just one carry look at. The problem is this, as we mentioned last time, is still going to have linearity, but it's still going to have fan in, fan out, too much current, spatial complexity, however you want to think of it. We just made it a little bit nicer than the truly ugly one that you got when you just all kind of stuff. So, but this is still going to fail. So we can only usually handle, like I said, the biggest ones I know. People, biggest, yes. But for example, the system, 8 to 12 is some of the sequence things like that. A few special, very functional ones will be able to handle 20. Yeah. Maybe they come out with some news in the past. Yeah. You're not getting you're not getting a fundamental order. You're not jumping up to 100 or something. You know, maybe somebody can push it to 28 and maybe 32 or something. Yeah. If you think about it, from each one of the lines coming in, they got to be able to handle it. We want to make these smaller. The smaller it is, the less it's going to be able to handle that current because your wire is getting smaller and smaller. It's a kind of a catch-22. Our goals are out. But this gives us our basic structure. So then what we need to do is talk about this. So let's spend a little bit of time on the algebra of this. We talked about this a little bit last time, but it's important to be able to specify this more. So let me actually start at, let's see, we'll say I've got a series of GIs and PIs. That's coming into me. So this is kind of given. I've got a whole bunch of these for I in the set of whatever, 0 all the way up to n minus 1. That fair? So I basically, I'm going to have, you have n bits. That's all I'm saying in this. And they're numbered 0 to n minus 1. So each one of these should put every bit, adding x0 with y0, and you've got g0 and p0. And you did x1 with y1 and a half adder, and you got g1 and p1. So on and so all the way down to n minus 1, the n bits. And many x's, a number of planes, to what the heck he's talking about. That's just this point here, right? Just take this, xi, yi goes into a half adder. The carry we call generate, and the sum bit coming out we're going to call propagate. That's all we need by that. All right. So I've got these for all of those different bits. I suppose I should put commas in there. Okay. So that's my input. I also have the carry in slash mode for the whole system. Whatever it is that particular stage. So, you told me I'm doing average, subtract, whatever. I have to have this bit. Good. Okay, we're going to do it, write it algebraically, and then we're going to go from there. So let's take a look. Carry 1, which is going to come from stage 0, right? This is the carry into the stage. So carry 1 was, did I generate something 0, right? Or did I propagate at 0 and there was something to propagate? I'm just going to use C short. This bit. Whatever. I wrote C in. So if I should get, we agree that that will generate what we want. Awesome. So this, fairly nice, right? There's an AND gate here. So this is 2 levels of logic. Great. So now we go to C2. Well, that is, I could have generated at 1, or I could have propagated at 1, whatever happened at C, right? Because now it's no longer Cn, it's C1. But C1 is G0. I'm just going to distribute. Maybe I'll do distribute on the next line. Use anybody at this point. P0 plus propagate 0 and Cn. All right, so all I did, I just advanced the next G1, P1. C1, and I just replace C1 with its definition. Good. Now I distribute because I don't want 1, 2, 3, 4 levels of logic. All right, so if I distribute, it'll take care of that problem. I'll get G1 or P1 and G0 or P1 and P0 Cn. Now I can have 1, 2. So I'm going to do there's all one a few cases that is useful for design. Not too much fastest, but yeah, it is still helpful in some places. So this is a good equation. This is a good equation. All right. So we were doing this last time. We're just going to do it specific because we want to generalize this. So C3 would be G2 or P2, right? And now I have to write the next one, which would be G1 or P1 and G0 or P1, P0, Cn. There. I again just advanced, took the same basic formula, generate at that level, propagate at that level, and whatever the previous C was, and I just substituted it. And again, there's 2 levels here, 2 levels here, that's 4 levels. Don't like that. Distribute. E2, A1, or E2, A1, G0, or P2, P1. And I'm back down to 2 levels of launch. Okay. Do we have a snap? Can anybody tell me from looking at this what CI plus 1 will be? So GI plus, yeah, times the CI, which, can you just tell me what that substitution will look like? Down to, yeah, so each one of these, it drops 1, right? So when we start thinking about this, we go, oh, this is basically 210, right? 2, 2, 1, 2, 1, 0, right? 2, 1, 0, CN, right? So it kind of is following a little pattern here. So you could say this is going to go up to whatever level in between this is, PI minus J, right? Times whatever the G at I minus J, right? You can get the little pattern that's slowing down. All the way down to like, yeah, so it's a summation of, do we agree with you? Each of these terms, if you just look at them, it's, you can get, the summation from, in this case, I'm actually going to sum up. So each one of these terms, it always starts at I, which is based off this. So I'm going to sum my thing on over my J term. All right, J is equal to 0 up to, and we eventually have to get to I, which is whatever our case is. All right. So I'm going to end up with a summation of terms that looks like a I. And now you have to think about what these I's are going to look like. All right. What's the pi for each term? Like, can you describe, well, we've got one here that actually hits our, right? All right, so this is going to run from I down to I minus j. And this should actually be so it's one. Yeah. So I need an index for this pi too, right? It's gonna have to multiply all those. So now I gotta have like a k. It's going to run from my I all the way to I minus j. Does that make sense? And that is of these pKs. So this will give me my series of i's. This has to then multiply my g at I minus j minus 1. Should be one less than whatever this is, right? And this will run through, right, when j is equal to 0. That'll give me I minus 1, so it starts with this term. So this explanation handles all this stuff in between, but it doesn't handle the CN one, and it doesn't handle this. Well, this is easy to add in, right? And if you wanted to, you could adjust your things so that the final index was higher. But I think it's easy to just explicitly. Fine. And this last one is just going to be the pi. It's going to be right from pi handed all the way down to p0. Right? So I need a j. In this case, um, I got a much nicer, easier one. It runs from I to 0. I guess you could do it backwards too. Um, of p, j, and that has to multiply c in. Let's see. That makes sense. Why? No. Sure. Oh, shit. So I could build this. Now the question is, I have students, right? Because I could theoretically let I get as high as I want, right? I now have a statement for CI plus 1, right? Can't be just students. Put this in a generate function plus the function that can be big, you're in problem spacing. So it's really made. So here's where things get fine. I could technically take what big problems your problem. Yeah. Yes. Feasibility. Yeah. So this is where simulation is very full thing. I just get the simulation and it shows me it works. Does that say now? That's why I have to be very careful with my constructs to make sure whatever you construct will correspond to what you build if you're able to build it. But that line of counter, if you're able to build it, still kills me on this one. Right? So what do I do? I take this idea. It's kind of so I think the thing that just kind of quickly generates this. So we the thing that I feel is how can we regulate the number of wires going in? I my first instinct is like, hey, can we watch this? So now we're getting into components. Well, it's going to have people that. Yeah. But you have some kind of track what they can do. It's going to make my complexity quite as nice as it was before. What if I do this in blocks? What I look at this, you tell me whatever you can take, 8, 16, 24, whatever. And I build up where it's my largest one your data point. Get big for what you have. So limiting the so limiting by. So I mean, I can make a block, and for that block, it will feed it. Yeah. Okay. So, for instance, let's just follow the idea first. We'll see where its issues get, and we'll see what we can do with it. I might have to go steal another sheet of paper. I grab three evidently. So imagine I could do something like this, right? Where I've got a bunch of blocks, right? A block, carry, look ahead. And this could be whatever size I want, right? Um, if I want 64 of these, would be 16, right? And I could generate that. I would have to ripple between them is one possibility. Right? But each of these things, we made two level check basically. So if by the time ripples through eight, if I'm doing 16 of these things, fine. 15 inputs coming into each one of these things. I can so become a limit of what you can handle. But I mean, I'm talking about and this plus a few extra logic levels, maybe 12 gates or something. So I've taken something that was hundreds of gates delay and taken it down to 12. That good? That's good. Is it the best? No, best. Fine. How did it escape? Wonder if do this. What about number hits? What's going to happen to the delay in this? Don't forget, all these go how many block here looking at. So, we'll have to go to eight. What we should eight. Nine. Each one of these is equal to 16. If I go to 128 gas, divided by 4, because I should say these are ADs, so 128 divided by 8, you know, you're going to get the, I mean, 8 of these things. I'm stuck, right? So, it was right. But fortunately, well, I got the dollars. So it's gone back to big old fan time. So technically, I'm just going to speed up on my ripple carry. Because it's base form, I'm rippling the carries between these blocks. Complexity wise, it hasn't. Now, again, in this case, it's getting 16 from 20. Now, jumping from 16 times 2 down to 2, right? Speed up of 16. The speed up of 16 good? That's just, think of it in books. And if I slowed your machine down by a factor of 16, you'd be happy with it. Now, so if the computer's studying this, they're still going to say your complexity stinks, right? And I'm going to have to say, yes, you know, but that means you don't care about 16 times speed. And technically, they don't, right? At least if you're a theoretician. In theory, this gives you no advantage. But the difference, in theory, there's no difference between theory and practice, and practice there is. I mean, if I got to choose something 16 times faster, you're going to but we're not done. I'd like to do better, right? So the problem is, I need to be able to predict those carries out of these block carries, right? So do we know a way to predict carries? here, look at it. What let me switch colors. That's the next one I saw. What if I have a pocket to generate from each of these? Uh, and I use that to generate the carry to the next level. Well, sorry. I agree. What's the question? I do. You can hook any two wires together. The problem is what does it do what you want? Yeah. So that's the big question. Can I go with wires? I can always, I, because it's wires that don't wall. That's all the difference. Let's say it's meaningful to talk about a generate and a propagate at this level for an law, right? So we're trying to figure out this little output here when we're making that assumption. The question is, can I sum this down, right? So let me call this, whatever, C star for power, right? So can I figure this out? Well, when will you get a C star? Type each. So, is the piece the you generate this on or the property is on. Generate turns on in the two bits and property is on when the cat is carried. So there is a one getting no, I don't. I've got a whole lot. I've been blocked a whole bunch of people. I, I call these G stars now just to again keep the stars for the next level, just so we can keep track of them. Right? Each one of these, the inputs is no longer X and Y, right? And it's a bunch of generates and propagates at each of these different levels, right? Um, this is a different set of numbers on here. So whatever J, generate J minus one and propagate at J minus one for the next two wires and dot, dot, dot. Right? Expression for what would be this G star. So I mean, I've got a way to pipe it in here, and I can generate the C star if I can figure out what these are. Well, what would guarantee that I got to generate out in terms of all of these elements? So if the very last stage had to generate, I would definitely, right, G star, right? If I had it, whatever that last stage was, GJ, right? Where J is how many bits you, right? It's four, you know, J is three. So it's four bits here, zero, two, three, right? So on and so forth. So J is just how that you're picking. I do it 16, J 16. So it's the very last one. If it generates, you've got to generate, right? If I have P, well, that's not, well, that is generate. Yes, you should get that P star, right? So what would P star be? PJ is true. Yeah. PJ. So PJ would have to propagate something from the previous level, right?
So
And that previous level, it would have, if it had a generate, would I get it? Would it? Well, actually, that is one thing that, actually, I should really put that up here. That would still generate, wouldn't it? If I had PJ and GJ. So would that still generate? Yeah, it would generate a carry. It would generate. So I shouldn't have put that there. I was right the first time writing it here. All right. So this will generate. If I have PJ and G, J minus one, right? My last stage will propagate and the previous stage generate. Will you get a generate? All right. What if my last stage will propagate and the previous stage will propagate and the one before that will generate?
okay, so we're getting the same summation.
Right? So I can do that for all of them until I eventually get or P, J, P, J minus one, dot, 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 all the way right down to propagate from my very lowest, or sorry, P1, right, and generate whatever the zero was. So we said one.
There's a carry.
But no generate. Because the carry in is going to be so much, so that's the problem. The carries go on the propagate, generates go on the generates. Would that actually handle generate whatever block size you have? Assuming you had this. Well, it's two, actually, right? One gate for getting in and a whole bunch of AND gates before feeding in, right? It's making it, right? They're good. But we should limiting the number of bits in there to whatever your gate could handle. Good, they do good, right? How about propagate? I started making this ugly, so let me just start this again. P star, right? I could, right? P, I would have to propagate J, but I'm going all the way down to propagating whatever came into it. So this is actually going to be a much easier term because, oops, it's supposed to be a J, not an I.
Okay.
Yes, every one of these has to propagate.
Yeah.
Right, well, that's the propagates, and you'll have the C later, right? Because remember the next stage, when we actually build the block here, look ahead, it does this, right? So we just need to know what was propagate, they'll add the C in. And they need to know what is our generate. Generate is this, right? So I could, this is a well-defined expression. It's I'm not saying it's tricky, I'm saying it's well-defined. Makes one, these are just two terms. G star as using one of my one of these. Yes, you can absolutely do that. Just like the previous one. It's by the way, it's also reuse of terms and what we built. Right? And P star is just all things expanded together. Right? So could I make a propagate and a generate out of each of the behavior? Yeah. Just present, just like I did with these and these and do that. So that's what's here, right? We're just taking a marker and looking at it. We're generating G's and P's. Each one of these generates its own little G star and P star.
Because you don't need to generate top.
This is going to combine is going to help the generates and propagates from the previous level. Does that make sense? So ultimately, this baby comes out this other end will be some generate and some but it's going to be made up of each one of these lines. We just have to combine them. Can you tell me in advance what this is? This block here. Even and almost it is the previous. So it's the same stupid blocks. It didn't just how big were those blocks for their block inputs. It just said, you tell me if it's going to generate or if it's going to propagate. No. You didn't care. You didn't know how many hits. You put that to us. So all we have to do is inputs. What's the structure look like? And it's a tree. And the tree is green. So logarithmic complexity. When a given tree is logarithmic complexity, because each one of these now, each unit is constant, right? And it doesn't matter how big, right? Because it create lineage to this tree, or lineage to this tree, but each layer is going to be 100% genuine unique to that. Make sense? Suppose so I think actually it's very been potential. This is reuse it. If you a for loop, even there, the derivative of a whole bunch of expression, I can still instantiate a whole bunch of these laws. So I'm making one block that will generate whatever size I tell them in advance, whatever it is, 4, 8, 16, 32. You tell me how big, how many wires can you take in, and I'll set the block size. And then I'll set the which I can do in another generator.
Okay, what's the time? The scale like it grows.
Time complexity wise, the generated network, at level, each block is now separated. Okay? So each of those blocks takes two. That's what we said, it's two levels of logic. And then the tree. So it is green. And it depends how big we make these blocks. Uh, just for the sake of argument, uh, let's say we get J is 4. You can handle 4 devices. Right? So I could have one. I'm just going to do square. It's my block here. I'll just put it once. I don't want to do this over and over again. I think this will handle 4 bits generated pairs. Now, if I go the extreme of this is when I get 4 of these, I need to have one more level. I'm not going to draw lines between them. I just want a simple thing. So this takes time of 2. This takes 2, 4 to generate. Fine. And technically, there's one extra thing here, but it's close enough. I'm not going to. Technically speaking, when you do it, you test the carriage. So I have to do 2 levels to generate it. Then I'll do 2 levels to make the next thing. It'll have to get integrated and then it's, but it's always just one more level. So technically it's fine, but I'm not going to sweat it. I just it's easier to see this. The progression growth is pretty darn nice, right? Each of the levels, this is how much time it's basically taking, right? Well, if I wanted to go, let me call this a rounded corner thing. This is one of these trees, right? If I and this will handle up to, you know, 4, 8, 12, 16. All right. Well, I could do one of these block of blocks, right? The rounded kind of block. All right. I could do 4 of those. All right. And I'm just going to break one of them out here, right? Which would be each one of these is made up of something that looks like this. Okay. I don't want to draw it, it's repeated on it.
So is it too big?
Right. Yeah. So now if you think about this as it's growing, well, how big is this thing? Because technically I could do this and have, you know, I could do the 4, I could do this, right? And run those into, this handles even more than just 4. I also need for this. For 4 of them, I just need 1 block. So that 3 gets me up to 4 times that. Right? And then another layer goes in. So if you watch what's happening, you know, 4, 16, 64 at 3 layers. When I go to 4 layers, 4 times 64, 256. So you can see the number of bits I'm handling is exponential to the layers. And the layers are right? 3 layers gets me 64 bits. 4 layers gets me 256 bits. I take on this case, I'm going to put logs are basically on the same scale. Adjust them, we will put a log ratio of the base pairs. Right? But you can see that every single time, the number of bits I can handle is 2 layers, in this case 4. 4 to 1 gives me 4. 4 to 2 gives me 16. 4 to 3 gives me 64. 4 to 4 gives me 256. The number of bits I can handle exponential to what the base is. That means the number of layers is logarithmic of the bits you want to handle. Bits you want to handle is the metric. That means this is long. Not, it's, it's not perfect. It's bigger. I'm going to do one thing that's long here. So now we're getting arithmetic time while maintaining our constant space. Um, I didn't do this. I get if I just hooked them straight and I cascaded them, I get linear time just, you know, constant space. Well, we have that. It's faster, that's good. Yeah. But now if you're really concerned about complexity of growth, I can get logarithmic time with linear space. Because it's using the same blocks at every level.
Yeah, sure. Which
Yeah, but each level is the same size as the previous level in terms of wires going into the gates. Right? Each one of these, at one point, at one here, just for simplicity, I'm adding generating. Right? So my gate in here are maximum of 5 input wires. Right? When I get to this level, this handles 4, 4, 4, 4. This handles. So I'm going to same size in there. So this handling at most 5 input wires per game. I'm reduced on the spatial complexity of the previous level, and I gave it an aggregate that represents correctly the behavior of the previous level. So it handles complexity more. right? So that timeline, you just have to work your way down through the list, right, to be able to get your answer. But the list is only logarithmic, how big this you want is. And each function here is constant in space. What we're concerned with identifying the space sometimes you this whole area, this whole thing is identifying it by how many wires come into each particular gauge or transistor. And why do I care about that? Because it's current. And current is counter heat. So this with a constant current density, constant heat density, that's what blows things up. Right? So space-wide, it's still not really that big, right? If you think about it, each level is long levels, and each level gets smaller. Okay? So even at that level, the growth of it is still, phase being so fast. It's a good trade. So my point to you is just can do. As far as really fast systems we do, this is did do some lab study for chips. We have historically done here, so here. So remember where you have those little chips, you have the NAND gates, and you have your stuff. Some people know. So yeah, it's been like I know we did when you did your stuff, we had like a day or two of it. At least for Marcia, because Marcia was telling me, right? I don't know if anybody else may have had, there was people who honestly here, right? So, I always hear things like, oh, we keep making people do individual chips. Now, here's the thing, I'm gonna at least look at some of the areas, because when you go to existing systems, that's kind of weird, like the higher tech stuff you're gonna find out there in general, space and cutting edge medical. I mean, that's the two areas I want in, and most of the time we use the oldest hardware. I now that might be very few yes, but there are two big reasons. Number one, older hardware have been tested. The likelihood of there being an error is very, very low. And number two, old hardware is big, so it's less likely to get an event offset due to radiation. And medical environments and space environments have a decent chance of radiation. And you don't want the smaller your device, the more likely one a um, X-ray, cosmic ray, or whatever else blocking it will cause what's called a single event offset. Right? And we care about those single event offsets because we put some minimums. The smaller your wire, the less current per wire, that means the less likely. Well, even at 74 measure series, to give you a perspective, it was invented before it was born. Okay? I got the already. So you can get thinking this is a benefit. We actually have your format and your it generates the P star and G star as well. So if block carrier is common and it handles 4 bits at a time, and it generates the next one. So you can do 3 cascades if you do. And if you think about it, that was you get the 60 minutes with 4 minute things. You can get the 64 minutes in 3 years. You never need to go more than, for vendor purposes, they need more than 3. You go for 64 bits, i.e. 3 years. So plenty fine system, right? And it's now instead of 64 bits, them having to do, the delay bits before dividing by 4. I do up what I've been a pretty decent area. They just have to do things. That's much better. 6 versus 16. So I'm just mentioning this just so you can be aware of this. And the fun thing is after our complete system, we need this and this. This is the output of each of my block area look aheads. And it is, I guess I should say, it also has a bunch of the CIs out you have to have along. So there's a core one that the 7400 series uses. It would do 4 carries coming out of the 4 bits that we're in. Right? So it's got a generator, a gate, and 4 carries coming out. And coming in would be 4 generators, gates, almost a little bit close to one the carry. And then you go, right? So that's the way it's going. So you can build those 3 boxes that I suppose here. You can actually write those and you can build your block area. You make it a module, called BCLA, so I think is one, and we express some of it's doable in a generate statement. So you have a generate inside a module that builds your block area locator. Now you have a block area locator. Now when you're in the aggregate, you can go pick a tree. You can either do this cascade ripple type, or you can do the tree. Just to make sure it's clear. Version. So first step is build on the BTL, test it, say hey, it's good. It's quick, but I got it. So now that you got that, and you should know you could hook those to be able to generate what you want. So now you can go blender taking layer or 2 layers of stage, even what if you get bigger than blender at? Build a tree of that. You can do that. You can generate statements. You're they just combine together as and they want in tree form. Get me one hand. Good. Guess what you got to do? Go to that tree form. Yay! All right. Tree form. So we're going to do this in 2 stages. First thing, you're going to build the one block area look at asset. You build the module. Don't worry about the trees. Just build the module. All right. You're going to build it specifically for gas. I want you to make it. That's what we want to do first. We'll build this and we'll test it. Right? We've only got like 10 minutes. So I'm going to leave it for you guys to start. I'll make sure you can start. Next one, like your best and just building a long-term local one that can build a single one. And then we'll talk about that. Because once we start like that unit, we can then talk about how we treat. Good. No good. Okay. So it'll take us to build this whole thing, but now you can start seeing if you can get new complexity, still managing awesome. Starting with that, I'm gonna stop this because nobody will be able to see it anyway. And then and we'll come around.